Let me briefly correct myself. In the previous video I said that the natural log of n was bigger than 1 over n for n bigger than 1. Of course, the natural log of e is 1, and so it would be past e, and of course if we're using integers that would be past 3. With that correction having been made, let's continue with the last portion of the lesson. There are two ingredients: the limit comparison test and then the second thing is an accuracy level if you're going to approximate. So if you're carrying out approximations to a certain number of terms, how accurate are you? And also, if you set an accuracy level, how many terms would you need? The limit comparison test is really the issue that your natural comparison causes the inequality to be the wrong direction. So for example, if we were comparing a sub n and b sub n, and it turns out that b sub n converges, it needs to be above, and that would force the one below it to converge. What if that's not the case? It's backwards from what you need. Well, then we resort to what's called the limit comparison test. Again, read the text for detail, but it comes down to the limit as n goes toward infinity of the nth term formulas. Really doesn't matter which one goes on top and which one goes on the bottom. But if that comes out to be a constant, and in fact a positive constant, then they behave the same. So if you know what the comparison does, you can claim the series you're wondering about behaves the same way. An example would be the series 1 over 2 to the n minus 1. The natural comparison for this would be the series 1 over 2 to the n. They look similar. The question is the comparison going to work? Well, if I look at the terms 2 to the n with a minus 1, the denominator is smaller, which actually means that the fraction is bigger than 1 over 2 to the n. So the inequality goes this direction. Problem is, we know that this series converges because it's geometric. If we think of it as 1/2 being raised to the nth power, r is 1/2. Since it's smaller than 1, it converges. And that means this series is a convergent. In order to force the other to be convergent, it would have to be bigger, but it's backwards from what we need. So when this happens, that the natural comparison, doesn't seem to meet the inequality need to carry out a regular comparison test, we resort to the limit comparison. Again, that is, take the limit as n goes toward infinity on the division of the two nth term formulas. It really, again, doesn't matter which one goes on top, which one goes on the bottom. I will put the 1 over 2 to the n in the numerator, 1 over 2 to the n minus 1 in the numerator, and 1 over 2 to the n in the denominator. Complex fraction, we invert and multiply. The 2 to the n goes to the top. That's the nth power, 2 to the n. And this is in the denominator, 2 to the n minus 1. Again, we're simply inverting and multiplying. Divide each of these terms by 2 to the n. So if I divide this by 2 to the n, I would get 1. If I divide this by 2 to the n, I get 1. And if I divide this by 2 to the n, I get 1 over 2 to the n. Thinking through the limit as n goes toward infinity, this term would head toward 0. And yes, we have a positive constant. And since that is greater than 0, and we ended up with a positive constant, we know that they behave the same. And so the summary of the limit comparison would be that since 1 over 2 to the n converges, the 1 over 2 to the n minus 1 behaves the same. It must also converge. Once again, that's because the limit of the nth term formulas headed toward a positive constant. Then they behave the same.